Welcome back. In the last video, we have completed the design of the SPI controller. We already simulated it and made sure it is working fine in simulation. Now, as I mentioned before, it is really difficult to test it directly on the board because your SPI controller that is also running at 100 megahertz. So if you want to see the signals, output signals, it is not still possible by connecting the output to LEDs because of the persistence of vision. But if you have access to some oscilloscope, maybe you can hook up them to the FPGA and see how the signals are changing. But Vivado and the Xilinx FPGA, they have a very powerful feature through which you can actually see signal in real time on your computer. Okay, so that's what we are going to see today. Now, this application is not only for seeing the output signal, you can see any internal signal in your design during runtime, and this is very useful in debugging. We spend a lot of time in simulation to find out all the bugs and correct them, but still there could be some corner cases which do not come up in simulation, and while you are testing the hardware, you find like your hardware is not working as expected, or sometimes your hardware is working, sometimes it is not working. So you really want to see what is happening inside the chip. Now, this scenario we discussed last semester for digital IC design also. So there we have the idea of scan chain insertion, I guess you remember, where we put a additional circuit within the chip and connect some key flip-flops to this chain, and during runtime you will be able to see what is happening with this flip-flop using a serial interface. So here also the concept is similar, but here the advantage is this scan chain insertion. Again, most of it is automated. You can decide which signal should be added to this chain in Vivado, and Vivado will be synthesizing that scan chain for you. So he will synthesize all the circuit for you, and during runtime you can specify special triggering condition under which he should be checking these outputs, and those output you can see in real time on your screen. So this data transmission, so at runtime he will be capturing the data from this flip-flop. That information is also sent through the same programming interface which you are using to program the bitstream as well as the ILA file. So all those things happen through the same JTAG interface. So this is a very powerful feature. So let's see how to do this. Okay, so in order to do this, the first step is you complete your design. Preferably you simulate it. After that you should synthesize your design. So I have already synthesized it to save some time. After synthesis, you should come under this option, setup debug. Okay, so come to setup debug and a wizard will come up. Using which you can be able to choose which signals you want to see in real time. For example, I am interested in all SPI output signals. So I am interested in SPI clock, SPI data, how they are changing during runtime. Okay, maybe all of the signals I am interested. So you should add these signals to this window. So to do that, you click on find nets to add, and here you can search for the particular net you would prefer to see it. Now remember, this step is happening after synthesis. So basically Vivado, he is going to search for these net names in the net list, not from your actual Verilog code. So you will find like the name that you have given in your code may not be matching with the name that you are going to see here, because the name here, they are the names in the source code, and after synthesis or during synthesis the tool is free to rename the nets, he is free to remove nets due to optimization, or he is even free to add new nets like register duplication and all. When that happens, he may be adding extra flip-flops and wires. So you may not find the names are exactly matching, but you can choose the one which are the closest matching. For example, I want to find every signal starting with SPI, so you can use a wildcard. Star SPI star means every signal which has something at the beginning followed by SPI, then something after SPI. Okay, so this is like our standard wildcard, and you can see two signals here: SPI underscore clock underscore obuff and SPI underscore data underscore obuff. You have SPI underscore clock and SPI underscore data in your design. Okay, you can see them, SPI clock and SPI data. But these two signals, SPI, these two signals, they are not coming from your Verilog source code. They are coming from the netlist. So if I go to the netlist, which is also under synthesis, so if you look at the schematic and if you look at the output, okay, this SPI underscore clock underscore obuff is actually the output of the obuff. So basically that is the name of this wire. Okay, this is SPI clock, which is a pin, and this is a net, which is this one. Okay, so when you're clicking the name here, the tool is automatically highlighting it. Where is that signal in the schematic? Okay, so you actually wanted to see these two things, but these two signals are exactly same as these things. Only difference is it is going through a buffer, and buffer, it does nothing to the logic value. So it's perfectly fine to view these signals instead of these two pins. So you should add them. Okay, SPI data underscore obuff and SPI clock underscore obuff. Okay, so I'm interested in these two. Then maybe I'm also interested to see this control signal, load data and send done. So remember these two control signal. Load data basically says like I want to send a new data through SPI to the SPI controller. Done send is basically the controller is telling me that he has finished sending it. So let's add them also. Load data star. Okay, so you can see like it's load data underscore ibuff. These are the wires coming from the input buffer. So if I go back and if I click it, where is load data? Okay, it's the output of this buffer, input buffer. Now here you can see it is showing something called undefined in red color. So one important thing to remember is every signal that you want to debug, okay, should be associated with a clock signal. So here you can see like he automatically saying these two signals, their values are changing in synchronous with this clock. And remember this clock that is there in your design, input clock, and this is the internal signal. Input clock goes through an input buffer, then it goes to a clock buffer. Okay, so this is same as the input clock in your design, this one. So he automatically found out these two signals are changing based on this clock, but he doesn't know what is the clock signal associated with this one, load data. Okay, since that is an external signal, as far as the tool is concerned, this is an asynchronous signal. So he doesn't know based on which clock this signal is changing. That's why it is showing undefined. Now the rule is every signal should be associated with a clock domain. Then only the debug circuit or your scan chain kind of thing, he can capture that data and send it to you. Okay, so he is going to capture the data using a clock signal. So you need to tell using which clock signal he should capture this signal. Okay, so you double click here on the clock domain, or I think you need to click here, more info. Okay, to show only nets do not have clock domain, and you can choose this one. assign all clock domain. When you choose it, he will list all the available clocks in your design. So currently we have only one clock, so choose that one. So what is going to happen is at runtime he is going to capture this signal, and he is going to capture this signal using the same clock, your input clock, which makes sense. Now I also want to see the done signal. Now done, remember, that is coming from the SPI controller, and that will be automatically captured using your clock, okay, your design clock. Maybe another signal that you are interested is this one, data in, so that you can check whether the input data is properly sent out. So I'm going to capture it. Now same issue will come. This is an input signal, so for the tool this is asynchronous, so he won't be knowing the clock domain, so you have to tell which is the clock domain. Okay, I think this one. You can directly click here and choose the clock domain there also. I guess we have almost done. So we have SPI clock, SPI data, load data, done signal, and buffer. Now the remaining one is reset. Okay, I'm not very interested in that signal. Load data, done. Yeah, that's it. Now one important thing to remember, never try to capture your input clock, okay, because the tool is going to use this clock to capture a particular signal. Now if you say you want to see this clock itself, that will be very problematic. For example, okay, clock underscore 10, you remember that's an internal clock, but this is your input clock. Now this is a serious issue. You want to see this clock, which is a clock, and you cannot capture that clock using the same clock. So never try to capture a sampling clock. Okay, so don't get confused. Here you are capturing SPI clock, which is not the sampling clock. Okay, this is not the clock used for sampling the signal. The signal used for sampling other signal is your input clock. So it's perfectly fine to capture SPI clock using this particular clock, but don't try to capture this clock using SPI. Now that's it. You can say next, and in this window what you are going to do is you are specifying how many samples should be collected before sending that information to your computer. So if you say 1024, is going to capture each of these signal on 1024 clocks. After that he will send that to you. Now you can increase the size. Okay, now one important thing to remember is the circuit which is going to capture this information and which will be sent to you. Okay, that circuit, Xilinx, they call it ILA, which stands for Integrated Logic Analyzer. From now onwards I will be just mentioning ILA or ILA. So remember, that is the circuit which can capture the internal circuits in real time. Now this is not a fixed circuit. Okay, this circuit is automatically inserted by Vivado into your netlist. So he will create a new circuit and he will integrate that circuit with the circuit that you have already built, and he will connect your signals with this ILA core automatically, and which will help you to capture it. Now since this is also implemented inside FPGA logic, the larger the sample size you specify here, the larger will be the size of this ILA circuit. Okay, so if you say, so this circuit is also going to build using LUTs, flip-flop, and block RAM. So if you increase the size too much, it will consume most of the FPGA, and sometimes what happens is there won't be any space for implementing your circuit. All the area is taken by this debug circuit. Okay, so we need to do it carefully. Again, that mostly comes from experience, how much data you need to capture under. For SPI, okay, 2048 or 1024 samples are more than enough, and you click next and just say finish. Now so he'll say like creating debug core. So he's basically designing the circuit which will be integrated with your circuit. Okay, now your circuit has changed. You should go and save And what happens is the information that you just added using that GUI, which signals to debug and which clock should be used for debugging, how many samples should be captured, those information are also get stored in the XDC file, Xilinx design constraint. Okay, save file saves that information also, which saves your pin information as well as the clock constraint. Okay, now suppose you are debugging some internal signal. That's it, you are done with everything. But for our particular case, we are debugging this input output signal to, so remember to give the pin location for the, so if you don't specify pin location for the topmost module, Vivado will give you error during bit gen. Okay, in the final step when you go for generate bit stream, Vivado will say like you didn't give location constraint, so I cannot build your circuit. So you should give pin constraint. So remember, so let's give pin constraint. So clock is our clock, well clock y9. Now send done is an output. Okay, so let me just assign it to a LED. So once send done is done, it will come to an LED, but most probably we won't be able to see it because things are happening so fast. But still, let me assign it. So I'm giving it to T22. Load data is an input that I will give to a push button. So I am going to give it to the center one, T16. Reset. Okay, let's give reset to the center one. Okay, it doesn't matter, you can give whatever you want. Okay, so load data, let me give it to the top button, which is T18. This one, let me give it to the middle one, P16. SPI clock, again SPI data, they are output, so let me just give it to two LEDs each. So T21 and U22. Okay, now data in. So this is where I specify what data I want to send. This I am going to give to my slide switches. So I have 8 slide switches. So what I'm going to do is, if I want to send some particular data, I will change my slide switches or your dip switches to a particular value, whichever I want to send. Then I will press this push button, which one? Load data, T18, the top push button. Then it will be sent over these two wires. That's the idea. Okay, so D0 is F22. This is G22. Same as before. H22. F21. H19. H18. H17. And M15. Again, M15, H17, H18, H19, F21, H22, G22, and F22. Remember to change the IU standard from default to LVCMOS 18. All of them. Otherwise, during bit gen, you will again get error. Okay, done. Save that also. That will be also saved in the same XDC file. Okay, so we have ILA core here, we have pin information here. Now come back to design, run. Okay, he's still saying synthesis is up to date, so no need to force update. Now go ahead and run implementation and generate bitstream, or directly click generate bitstream. Now this is going to take far more time this time. because now Vivado has to create this debug circuit, and he need to integrate that circuit with your circuit, so it is going to take quite some time. Okay, so we have completed our bitstream generation. So as usual, we program the board. Okay, now during programming, before you have seen only the bit file. Now once you add this ILA core, the debug core, you will see two files are there. There is a 1-bit file and there is a file with extension .ltx. Now this is the file which has the information about which signals you are going to debug. Okay, only this file is sent to the FPGA. This file is kept locally so that when you run your board, and when the board sends the debug information to Vivado, he can find out to which signals this debug information belongs to, and he can show it in a nice waveform. Okay, that is what this file is doing. This is not going to FPGA, this is kept locally, but you need to specify this file also, otherwise when you view the waves, there won't be any name to the waves. Okay, this file has the information about the name of the debug signals that you have added. Okay, so choose it and program. Now once you program, unlike before, now you will get this window also. Okay, this looks like a simulation waveform window. No, that is not the case. This is the debug window, and you will see the internal signal in real time in this wave window. And on this tab, if you see, now you will see under this FPGA name, hardware underscore ILA underscore 1. This is the debug code that you inserted to your design. That is also listed. And in the window, you can, this is coming from that LTX file. He automatically lists all the signals that you chose for debugging, and zoom in, zoom out, everything you can do, same as the simulation window. Now, if you want to see what is the current status of the signals, okay, you want to immediately view what is the current status of these signals inside FPGA, you just click on this button, run trigger immediate for ILA core. You click it. It will take few seconds because the debug core, it need to capture this signal. We specified 2048, so he need to collect 2048 samples and send it to your computer through the JTAG interface. So that's going to take a few seconds. So it is not very real time, but real enough. Okay, and you can see the current status here. So it's showing like all input data is 0, SPI data output is 1, SPI clock output is 1, and load is 0, done is 0. And so let's see whether our code is really working on board. My camera is not so great. So you can see two LEDs are constantly on. Okay, these two LEDs correspond to the serial clock and the serial data that we assign. And remember, when the clock is not active, it will be always 1, and when the data is not active, it can be 1 or 0 depending upon the previous state. Anyway, these are the 4 slide switches which are used for specifying the input data. Okay, and currently all of them are in off state. What I'm going to do is I'm going to turn 4 of them on. Okay, the 4 lower bits. So currently my data is 1111 sorry 00001111. Okay, so this is my data in. Now if I press the upper button, which is load data, this data should be sent over the SPI link. Okay, so that's what our design is. Let's come back here and let me quickly do one thing. Let me click this button and see what is the current status of the signal. And now you can see data in buff is showing 0f. So this value is also in hex. And remember from where this is coming. This is coming from data in, which is actually connected to my slide switches. So when I change the slide switches, this is also changing. Now let me turn all of them on, all 8, and let me run it, and you will see it became FF. Okay, so this shows like this is actually capturing the input data. Now this is not very useful. Okay, what you need to see is the actual SPI data transmission. Now how can you do it? So that is done the same way it is done in oscilloscope. So I guess you know about triggering in oscilloscope. So there is an option called triggering in oscilloscope where you can specify some condition under which the oscilloscope should capture the data. So here also the concept is same. You need to specify a condition to the debug core, and if that condition happens, he will capture 2048 samples of all these debug signal and send it to you, and you can visualize it here. Okay, so here also you need to specify the condition for capturing the data. Otherwise each time you have to manually press it, and it is impossible to press this button at the exact same time while SPI data transmission happens. It's not possible, right? So you need to set it using so-called the trigger condition. So for that you need to come to this window, trigger setup, and there's a plus sign here, and when you press it, he will again show all these signals. Okay, now what is the condition, what is the best condition to see SPI data transmission? I will say when my load data, when this signal goes from low to high, okay, when this signal becomes active, that is the signal for SPI data transmission. So if I start capturing data when this signal goes from low to high, I can see what is happening after that certain condition, that specific condition. So I should be able to see what happens when the signal goes low to high. That is when my controller is supposed to send data. So I will choose this signal. Again, how you do it depends upon your particular application. So you need to find out which is the appropriate condition for capturing the data. Again, that you learn from experience, and you need to add it here. So I'm choosing this one, load data, and there's an option here, value. I'm setting it rise 0 to 1. Okay, so what I'm basically saying is when the load data signal rises, when the signal goes from low to high, start capturing data. Okay, and I know that this is the condition for starting an SPI transmission. So if I start capturing data when this condition happens, I will be able to see how data gets transmitted through SPI by looking at the other signal. Okay, so this is one condition you need to do. Now on the left, there are a few options. One is the settings. Okay, there only one option is interesting, the trigger position. Okay, so this is basically the trigger. This is what we call as a trigger, the condition for capturing the data. Here, trigger position window, here you are specifying how much data should be captured before this condition happens and how much data should be captured after this condition happens. Again, this is same as oscilloscope. So these are the pre-trigger condition. Okay, sometimes you are interested to see what happens before this particular condition happens. In some cases you are interested to see what happens after this condition happens, and sometimes you want to see both cases. What happens before this condition happens, what happens after this condition happens. So based on that, you can set the trigger position. So if I set it to 1024, that means I will capture 1024 samples before this condition happens and 1024 samples after this condition happens. For our application, this is perfectly fine. Now, there are cases where pre-trigger doesn't make much sense. Even in our case, pre-trigger means capturing data before this condition happens. It doesn't make much sense. What I'm interested is what happens after this happens. So maybe it's perfectly fine to put it to 0 even, or 10. That means I will capture 10 before this condition and 2038. So remember, our total capture size is 2048, which we set when we chose the debug option last time. Okay, so if I set 10 here, 10 samples before this condition, 2038 samples after this condition. So again, depends on the application. You can choose the appropriate value. I'm putting it back to 1024. Now when he actually captures the data, you will see the window here, that information in the window here, and in the window you will see this marker, the trigger marker. So this marker is basically saying where this condition happened. Okay, so you will have 1024 samples before this condition, 1024 samples after this condition. Okay, so you need to do this much setup. You need to set the trigger, you need to set the trigger position. Okay, now once you have done that much, we are ready. Actually, you need to click this option. So previously we were clicking this one. If you click this one, he will immediately capture data and show it to you here. Now if you click this one, he will wait for this particular condition to happen, and only when that condition happens, he will send data here and will be displayed to you. Now let me change my input data slide position to 1010 and 1101. Okay, so let me quickly show you that is the case. So my data here is AD, which is 10101101. That is the condition I set on the slide switches. Now I am pressing this button. So we basically say we are arming the ILA logic analyzer. And if you come to this one, status tab here, you will see like it will say core status. This is the status of the debug core inside the FPGA. He is waiting for the trigger. He is waiting for this condition to happen. So that condition has not happened. Okay, that condition has not happened. He is waiting for that to happen. If that happens, he will capture the data and show that to you. Okay, so now let me press the upper push button, which was connected to the load data signal. Okay, I'm going to press it. I pressed it. As soon as I press it, you will say like capturing. He will show a print here, and you can see the wave window got updated. Okay, and you can see how the signals are changing. So this is where this condition happened. So if I zoom in, you can see this is where the point load data went high. Immediately after that, my clock and data are changing. Let's see whether it is happening in proper way. So we need to look at the rising edge. What data I am seeing? I am seeing 1 0 1 0 1 1 0 1, which is exactly this one. So remember, in SPI we need to send most significant MS bit first. So the order should be 1 0 1 0 1 1 0 1, and that is what is exactly happening here. And once that happens, you can see done send, that signal also went up. Okay, so I can say with confidence now my circuit is functioning properly on the hardware. Okay, now let's come back to our debug core insertion. So as I mentioned before, sometimes what happens is Vivado during synthesis, he will optimize your code, and it is possible that he will remove some of your signal. He may rename some of your signal such that when you try to add these signals to debug, you won't be able to see them. Okay. For example, let me take the debug core once again, and since you already have a debug core, okay, this time when you start this window, he's saying like continue debugging 12 nets connected to existing debug core. You already have 12 nets. He's asking you whether you want to keep them and add additional one or edit them, or you want to remove all of them and start fresh. Okay, so maybe we can continue with the existing one. Okay, so I'll go next. So these are the existing one. Now what I'm interested is I want to see the state transition. So I have a variable state here, right, which is storing the current state of my system. It is basically nothing but two flip-flops. Okay, two flip-flop that is actually saying the state of my system. I want to see how the states are changing, and most system which have state machine, one of the interesting signal to add for debugging is state. And you can also see this is an internal signal. This is not an input output signal. This is some signal inside your design. Okay, most of the signal he will preserve. For example, I want to see this counter, so I can go here and just search for counter, and see he's showing counter here, which is same as counter. This 3 in the bracket is basically saying it's a 3-bit counter, which is exactly same as this one. Or you want to see how this data count changes, so you can search for data count, and he's here. You can directly add it, no issue. But when I'm trying to add state, yeah, state is there, you can see it, but Vivado, he has completely changed the state variable. Okay, so you simply declared it state, but he has renamed it to something like fsm underscore one hot underscore state 0 and all, and there are many signals. So now I have no clue like how these signals here correspond to my 2 bits here, because here I can see many. It is not only 0 and 1, it is like 0 2 3 3 3 and all. So I have no clue how they are related. So if I add these signals to my debug core and if I view them, it's really difficult to find out what is happening. Okay, now Vivado, he has the capability to analyze your design and find out whether you have a state machine if you write it in a proper way, and he has specific optimization for state machine to make it a better state machine. That's what he has done. Okay, so he has done something called one hot encoding for state machine. I don't know, have you heard about it before? In digital, I hope you have heard one hot encoding. That means in the state variable, only one bit remain high and everything will be 0. You can go and check it up. So he found there is a state machine. I have a state machine, and the best way to encode my state machine is using something called one hot. So that's what he has done. Now the problem is, because of that mapping, I'm not able to add it to my debug and find out what is happening. So what I would prefer is I need to maintain the same signal name. I don't want to change my signal name so that I can easily debug them. Okay, so I need to tell Vivado that don't change my signal name, preserve it as such so that I can debug it. Now that is very helpful in debugging, but once you find the problem and do all kind of debugging, you should let Vivado to do whatever he wants to do. Otherwise, that may affect the performance of your circuit. Okay, you are putting a constraint like he cannot completely optimize your circuit, so you don't want to do it. But during debugging, we are not worried about performance. We are worried about the functional correctness. So at this time, what I want to tell him is don't change my signal name. Now, to do that, we use something called attributes. Okay, in Verilog you haven't seen attributes before. They may look like comments, but they are not comments. For example, you always write attributes in parentheses followed by star, then some attribute, then star parenthesis. This is the syntax. So here I am using a specific attribute called keep. Okay, keep equal to true. So whichever signal you want to preserve, whichever signal you don't want Vivado to modify, you need to add this line just before where that signal is declared. So I want to preserve state, so I'm just adding it here. Okay, so this line is going to affect only the declaration below that, only one line of declaration below that. So it's not going to affect these two guys. If you want to preserve them, you need to add before their declaration. Now comments, comments are usually ignored by your tool. Doesn't matter which tool, you'll simply ignore all the comments. But this attributes, this is some information to the implementation tool, in our case Vivado, and this is telling Vivado you need to preserve this signal. Now these attributes, they have nothing to do with Verilog. Attribute syntax has to do with Verilog, but this keep, okay, keep is a type of attribute that has nothing to do with Verilog. So what all attributes are available depends upon the particular software you are using. So this keep attribute is understood only by Vivado software. If you use keep attribute in Quartus, the other one for Intel, he might not understand. He will have some other attribute which Quartus understand. Okay, so keep that in mind. So I'm adding this attribute now. Now since I changed my Verilog code, have to go from synthesis again. So I have to resynthesize again. And once synthesized, again go to the debug and check whether the variable is preserved or not. Okay, synthesis is completed. So choose open synthesize design. Okay, or you can directly click here, open synthesize design. Now let's go to debug once again. Keep alternates. Now let me try to find, let me search for state, and here it is. So state 2-bit, which is exactly the way how I declared. Now I can add it to my debug signal and go to implementation with stringent, then program and do debugging. Okay, so this is a very good feature. This is one of the most powerful, most useful features for Xilinx and Vivado, this in-system debugging. You will have to use it under many scenarios. Even if your simulation is working perfectly, many cases the system may not be working consistently. You will find like sometimes it's not working, sometimes it's working, and again it's your experience based on which you determine which signals should be added to the debug code, so and which trigger condition you should set so that you can find what is going wrong. So that's based on experience, based on practice. You will have better idea like which are the possible signals for debugging. Okay, so that concludes our tutorial. If you're interested, you can go ahead and implement it and test it with the state variable. Yeah, it will definitely work. Okay, thank you.